All right. So we're in the middle of series. So we got series. Remember what a series is it's an infinite sum. The way we define series is we take the limit of finite sums. So the S sub n is called the nth partial sum. And so from the sum we get a sequence of partial sums. So take the limit of the sequence of the partial sums. That's what we assign to the value for the infinite series. In some nice cases, we can actually find out if it converges what it converges to, but most of the time we don't. The big tools we have for determining whether or not the series adds up to something, we've got the divergence test, which is a test for divergence only. It says if the limit as k goes to infinity of a sub k is not 0, then we can be guaranteed that the series does what? Diverges. It's right in the name. If, on the other hand, the limit as k goes to infinity of a sub k is 0, then we don't know what's happening. It could either converge or diverge. Once again, divergence test, typically very quick to apply, but it doesn't give you the complete story. If the limit isn't 0, it diverges for sure. If it is 0, we don't know what goes on. We had geometric series. We can spot them by looking at the ratio of ak plus 1 over ak. Oftentimes it's easier to write them as reciprocals. If the absolute value of r is less than 1, the series converges. Otherwise, the series will diverge. So once again, geometric series, typically easy to spot because the k's are up in the exponents. If k's are if all you have are k's in the exponents, you want to run it through, make sure it's geometric. You can apply the test. The other series that we know about are p series. P is bigger than 1, it converges. P is less than or equal to 1, diverges. So once again, what's nice about the p series is when you have it and you identify it as a p series, you know if it converges or not. Right? So that's what's nice about geometric and the p series. The next big star is the limit comparison test. So since geometric series and p series are pretty easy to spot, limit comparison test is like, hey, if the series you have maybe isn't quite a p series or isn't quite a geometric series, but if in the limit it sure looks like one, then you can use limit comparison test. So limit comparison test, number one, it works for positive series terms. So you need positive series terms, and you look at the limit as k goes to infinity of ak over bk. If this works out to be L, a finite positive number, both the series, or I should say AK the series of AK and BK either both converge or both diverge. Essentially what we're saying is that the terms AK and BK go to 0 at roughly the same rate. So whatever the one does, the other one has to do. And then we have a couple other cases. What if the limit is 0? What if the limit is infinity? So if the limit is 0 and I know that the denominator converges, then I get that the numerator converges. Because in this scenario, AK is getting to 0 faster than the BK is. If the BK goes to 0 fast enough to converge, then definitely then the series, the AK, will converge. If, on the other hand, the limit AK, BK goes off to infinity, and the denominator diverges, then the numerator diverges as well. Now, the other tests we've talked about thus far, direct comparison test, integral test, they have their niche, okay? But usually they require more conditions to apply. If you think about this one from the test, we had like 1 over k squared minus k. With the limit comparison test, you wouldn't bother doing partial fractions anymore. You follow? If all you want to do is figure out if it converges or not, you can compare it to what test? Who's running the show in the denominator? The k squared or the k? K squared. So you could do a limit comparison test on that. You with me or not? Now, it won't tell you what it adds up to. The nice thing about the way we did it on the test is you know it adds up to what maybe it was what, 4? I guess it was 4. All right. The thing about the integral test, the limit comparison test, and the direct comparison test is all of those series have to have positive terms. Right? They couldn't have negatives in there. So today we're going to talk about alternating series. And we talked about alternating series before. The word alternating means they alternate between plus and minus. Okay? And so the poster child here for the alternating series is the alternating harmonic series. Now we know the harmonic series on its own blows up. Right? It's P series. In fact, we proved the harmonic series blew up using integrals, which led us to the integral test. But here's the alternating harmonic series. The divergence test will fail because as k races off to infinity, even though you're bouncing around between minus 1 over k and 1 over k. The squeeze theorem is going to squeeze those terms to 0. And if the limit of the kth term goes to 0, divergence test doesn't tell you anything. You follow? It tells you nothing. And as I mentioned, the other big power tools we've used require the terms to always be positive, and these aren't, right? Every other term is negative. So what do? We go back to the definition. Okay? And so this is going to be the third time we've had to go back to the definition, look at the partial sums, and appeal to the completeness of the real numbers. But let's look at the partial sums. So here they are. So we've got the odd numbered partial sums here and the even number partial sums here. Once again, S1 means you add up the first term. S2, you add up the first two terms. S3, first three terms, and so on. We all cool with that? And then we're just going to rewrite some of these even terms. Let's look at S6. S6 is going to be 1 plus, and then I'm going to just group these together. I'm subtracting a half, you follow? And I'm adding back what? A third. I'm adding back less than I'm subtracting off, you follow? So this is still going to be what kind of number here? A negative. And now let's look at minus a fourth plus a fifth. I'm subtracting off a fourth, I'm adding back a what? Fifth. Am I adding back as much as I'm taking away? No. I'm adding back less. So that's going to be a what? Negative. And this is a negative. And so we can see that this is all, that's less than 1. You follow? And you can make that argument for any of these evens. Because look, this is going to be less than 1. Here we can group these together and have that one. That's going to be less than 1. Here we can group these together. You with me or not? So if you look at the even partial sums, they're all going to be less than 1. Fancy speak, that means they're bounded above by 1. Right? Now let's rewrite them this way. I got 1 minus a half. So if I look at it this way, let's go up here. So 1 minus a half, 1 minus a half, third minus a quarter. So that's S1, or that's S2 rather. I could write this as S2 plus, what kind of number is this? A positive number. You follow? So that means that S4 is going to be bigger than S2. You follow? Now I look down here, and I got this and this. That's S4, and I'm going to add this on it. You with me? But a fifth minus a sixth is what kind of number? A positive. And you can continue this pattern to get that all of the even partial sums are also increasing. You with me or not? So the even partial sums, they are bounded above by 1, and they are increasing. So that means that the even partial sums converge. We have an increasing sequence that's bounded above. We talked about this, I guess it was a week ago Monday. If you have an increasing sequence bounded above, that sequence will converge to the least upper bound. So this is the third time we've actually seen this. And that property of the real numbers is always in the background making this work. All right. So I know that the limit as n goes to infinity of the even partial sums is some number. I'm going to call it L. You follow? So now the question is, well, what about the odd partial sums? So let's look at the difference between the odd partial sum and the even partial sum. Right? So to go from 1 to S1 to S2, I'm just adding on this. Go from S3 to S4, I'm just adding on this. S5 to S6, I'm adding on this. You follow? So once again, we've got this little situation where if I look at the difference, between the even and the odd, I should say the adjacent ones, you just get we just get that term. But these terms are going where? Well, we know from when we tried the divergence test, these terms are going to where? 0. So the even numbers are going, the even partial sums are going somewhere. The difference between the even partial sums and the odd partial sums is going to 0. That means that the odd partial sums have to be going to the same place. Does that make sense or not? Okay, and that's pretty much the proof. So if I look at the limit as n goes to infinity between the even partial sum and then the odd partial sum, that goes to 0, so this shows that the even partial sums go to the same place as the odd partial sums. And that means that the original series converges because the partial sums converge to some number. And so this has everything recorded here. This is the more precise notation, what we're talking about. The odd sum is equal to the even sum plus 1 over 2k. And we take the limit as you go to 0, and so there it is. So if we go back and look at what made this argument work, there were 3 things at play here. Number 1, we had an alternating series. When you have an alternating series, you subtract and then you add back. You subtract and then you add back. So that was an important thing. We needed to have it so that the stuff that you added back was less than the stuff that you subtracted. If I just take the negatives out, they had to be decreasing. And then I needed to make sure for the even and odd partial sums to go to the same place, I needed the individual terms to go to 0. So if you do this argument, but just in general with those 3 properties, you get the alternating series test. Here it is. So the alternating series test. Suppose you have an alternating series. Once again, it's right in the name. You need an alternating series to apply this. If the terms themselves, ignoring the plus or minus, is a decreasing sequence that goes to 0, so these are the terms we're talking about, then the original series converges. So remember, the divergence test was a test for divergence. The alternating series test is a test for convergence. If you apply the alternating series test and it works, your answer is convergent. It's never divergent. You can never say this diverges by the alternating series test. Okay. That being said, this is a partial converse to the divergence test because we have the limit going to 0, but then you throw in 2 other conditions, and that'll give you that it converges. Because normally if the limit is 0, it tells you nothing. Well, here the limit is 0 plus a couple other things. You get converged. So let's actually apply the AST to the harmonic series to see how it gets used. And then here's a video, once again, that you can watch. And once again, I caution you, you want to do the book homework. Book homework's great. But when, like on the test and stuff, if you say this diverges, I mean, you could coin flip, converge, diverge. I'm looking for the little reasoning, okay? So this is how we would go through and apply the alternating series test to this sequence. All right. First off, we have an alternating series. Because you got that -1 to the k plus 1. Now, once again, word of caution, just because you have a -1 to the power doesn't always mean it's going to alternate. Is this the one? So, in the privacy of your own home, write out that one and see what happens. So it does alternate. Boom. 2. Now, we look at the a sub k's here, in the alternating series test, the a sub k's are not the terms themselves. They're the positive positive parts of the term. So they're basically the terms ignoring the signs. So the a sub k would be the absolute value of these things, which would be the 1 over k. So I have two things to verify. Number one, I need to know that the limit as k goes to infinity of the ak is 0. There it is. So this is the only situation where the kth term going to 0 is part of the test. You follow? And then 2, I need to know that the ak are decreasing. So I need to know, is a sub k plus 1 less than a sub k? So you look at a sub k plus 1. And how do I know 1 over k plus 1 is less than 1 over k? We got the same numerator, but a bigger what? Denominator. So that'll work. Okay. So this is all you need. You need an alternating series where the positive parts decrease to 0. The alternating series says converges. So by the AST, the alternating series here converges. Okay. But you have to go through each of those parts. You follow? You got to verify all those hypotheses. And so we go through. There's a couple more examples for you to look at. And once again, these kind of model what I expect to see on a take-home or the test with these. All right, here's another nice thing about the alternating series test. Remember, you never get back what you took away in the first place. You follow? So this is especially helpful when we're looking at remainder theorems. So once again, if you have something, if you've got a test that satisfies the alternating series test, it will always converge, right? If it satisfies the alternating series test conditions, that series is going to converge. So we have a nice little remainder theorem. So let's remember what remainders are. So I think of a series as being an infinite sum. Let's say we add up to an and then we move on forever. The sum of the first n terms is what we've been calling the nth partial sum. And then the sum of the rest is what we've been calling the remainder. You follow? Now, in the case of our alternating series, the alternating series, your remainder is going to look something like this. You with me or not? Okay. Or maybe it's the first one that's negative and the second one's positive. Doesn't matter. We're going to take the absolute value of this anyway. And here's where we're going to use the result that because of the fact that those individual ANs are decreasing, you're taking away AN plus 2 and you're adding back AN plus 3. You're not adding back as much as you took away. You follow? So it's going to be less than AN plus 1. And then continue so on and so forth. So this is always going to be less than or equal to AN plus 1. And so the remainder theorem for the alternating series test, I like to think of it as your error or your remainder is always less than or equal to the first neglected term. The first term that you didn't add in is going to be a bound for your remainder. So So this is the big remainder theorem here. The error incurred by approximating the sum of the series, which converges by the AST, is bounded by the absolute value of the first neglected term. So let's do an example. Consider the series. Sum k goes from 1 to infinity of negative 1 to the k plus 1 divided by k squared. First thing says to prove this series converges using the alternating series test. Okay? The first thing you have to show, if you're going to use the alternating series test, is the series what? Alternating. The best way to do that is when in doubt, write it out. So when k is 1, I get negative 1 to the squared, which is what? Positive 1. When k is 2, I get negative 1 cubed, which is you follow? So we do have an alternating series. And now we look at the a sub k's. Remember, in the language of the alternating series, the AK is the positive parts. So it's the absolute value of these terms. And I look for the limit. These terms have to be decreasing to 0. So if I look at the limit as k goes to infinity of 1 over k squared, does that go to 0? Yep. And now let's look. Is AK plus 1 less than AK? Well, one way to do that is to actually just look to see what we have. Yep. We got the same numerator, bigger denominator. So all of this together says that the series converges by the AST. You need an alternating series. You take the positive parts, they decrease to 0. Any questions on what you need to show for the AST? You good with that? Approximate the sum using S10. Okay, we're going to use Desmos for this, right? My intention for you, especially during the summer, is for not to sit down and do a bunch of this arithmetic by hand. I think that's cruel. So let's go over to Desmos. So we want the sum. So we'll type in SUM, and we use the counter k. Doesn't matter. K goes from 1 to, and we want to go up to what? 10. First part, 10 terms. Negative 1 to the k plus 1 over k squared. And we get that. Is that what I have written down? 0.8179, blah, blah, blah. We good with that? Okay. Now the question is, what's the approximate error? So now what's R10? So the error here, I'll put it this way. The error here would be the actual value of the remainder, R10. You follow? And if I knew what the error actually was, then I wouldn't really have an error, would I? So the best thing we can do is bound it. So the absolute value of the error is the absolute value of R10, which is going to be bounded by the absolute value of the first neglected term. So what's the first neglected term? S sub 10, I added up the first how many? So the first one would be the A11, which would be the absolute value of negative 1 to the 12th over 11 squared. That's 1 over 121. Make sense or not, folks? And that's it. That's why I love this remainder theorem. You just go one more, and that's the worst error you could get. Make sense or not, folks? Now, what if you wanted the error to be less than 0.0001? You follow? So what if I wanted the error to be like that? What would you have to do? Well, you'd have to figure out the absolute value a sub k plus 1 would have to be less than 0.0001. So 1 over k plus 1 squared would have to be 0.001. And then you can multiply and do the nonsense. K plus 1 squared would have to be bigger than, what, 1,000? So that would be 32 and change. So k would have to be at least what? 33. You follow or not, folks? And so you would look at S33. I'm just going to pop up here, put a 33 in there, boom. And then for fun, we'll test the limits, pun intended, of Desmos here. Let's put like 1,000 up there. So as you keep putting zeros, you can see there's the 0.8229 blah blah blah. Down here it's what? 0.822. You follow? So the error is within 0.001. Okay. So just like the remainder theorem on integral test, you can reverse engineer the remainder theorem on this. All right, absolute and conditional convergence. So once again, the divergence test will work on anything, whether you've got positive or negative terms. But a lot of the big power tools we've been using, you have to have positive term series. Alternating series is great, but the series has to alternate plus and minus, and not all series are going to do that. So we talk about the concept of absolutely convergent. So a series is called absolutely convergent if the sum of the series of the absolute values converges. Now notice here, we're taking the absolute values and then adding them up. You follow? So for example, if I look at the series k goes from 1 to infinity of the absolute value of this is the one we were looking at. That's the sum k goes from 1 to infinity of 1 over k squared. Is this series convergent? Hopefully you recognize this is a what? P series. What's P? 2, which is bigger than 1. So it converges. So we use the word absolutely convergent because the series of the absolute values converges. You follow? That's absolutely convergent. What about this next character? You take the absolute values there. The k is already positive. The negative 1 is going to become a what? Positive 1. And that's the harmonic series. This is the divergent harmonic series. Or you could say it's a P series. P is 1 less than or equal to 1. Either way. So this would be not absolutely convergent. So when we look at absolute convergence, we're looking at the absolute value of the individual terms and then adding them up. So if you looked at this example here, the series itself was convergent. So the series itself converges by the AST, but the series of the absolute values diverged. So a series that does that is called conditionally convergent. So if the series itself converges, but if you take the absolute value and then add, it blows up, it's called conditionally convergent. So the question is, what could we have the opposite situation? So we have the situation where the series itself converges, but the series of its absolute values don't. Is it possible to have the series of absolute values converge, but the original one not? And the answer is no. That's our absolute convergence theorem. If the sum of the absolute values converges, then so does the original. So if you have a series and it's got positive and negative terms in it, you take the absolute values. If that converges, then you're done. The original one converges as well. So I like to think of it, does it converge? Absolutely. You follow? You see, it's a play on the words. The proof of this is actually quite nice. It starts off with this inequality. You take the terms plus their absolute values. Remember, when you take the absolute value of a term, you either get the term back or you get its opposite. You follow? So you either get 0 if they cancel out, or they double up if they're both positive. You follow? Now, if we assume that the absolute value series converges, then 2 times it also converges, because 2 times a finite number is a finite number. And now we're all set up for the direct comparison test. So if the absolute value series converges, and so does this one, by direct comparison test, so does that. And now we use properties of convergent series. We're going to take this convergent series minus this convergent series, and look what's left. If you take this minus this, you get what? The original. So it's a nice little proof. Once again, the direct comparison test comes in when it needs to come in to fix it for us. So that means in your headcanon here, when it comes to all series fall into 2 big categories. You've got the convergent series here, and you got the divergent series here. Within the convergent series category, you've got your absolutely convergent series, and you've got your conditionally convergent series. If the series you're given is already all positive and you show it converges, then it's absolutely convergent just because it's already all positive. You follow? So the absolute convergence theorem really helps when you have series, like for example, let's look at the series k goes from 1 to infinity of -1 to the k over k cubed. Could you use alternating series test on this? Yeah, it would work. AST works. But you could also try absolute convergence. Because when you take the absolute value, what's going to happen to that -1? It's gone. And now we can quickly see this is a what? It's a P series. What's the P? And what's important about 3? So it what? Converges. So that means that the original series converges absolutely, and that might be a little faster. You with me or not? Plus you get more information. Okay. So once again, here's a video example for you to work through. What type of series is number 1? How good are you getting at spotting these? Number 1 is a what? It's a geometric series. So let's take a look at this one. So we've got that cosine up there, and cosine always flops around, but the denominator is getting what? Bigger and bigger and bigger. And because cosine is cosine, sometimes it's positive, sometimes it's what? Negative. But it doesn't do it in a pattern. Let's make a table. So you do get some positives and some negatives, but do they follow a pattern? Is it alternating? No. So on this series, you're kind of locked into trying absolute convergence because you can't try any. The divergence test, the individual terms go to 0 because cosine is trapped between -1 and 1 and the denominator is blowing up. Divergence test will fail. The other tests require positive series terms. Alternating series requires terms that alternate. This one doesn't. So the absolute convergence test is the only hope here we have for this. So we're going 1 to infinity. Cosine of 2k. Whoops. K root k. So we'll try the absolute convergence test. We'll look at the sum. K goes from 1 to infinity. Absolute value. Cosine of 2k over k root k. K's are all positive. We only need the absolute value on that. And this is the classic direct comparison test. What can you tell me about k root k? It's the same as what series? K to the what power? 3/2. So what kind of series is it? P series? What's the power of P? 3/2. What's important about 3/2? Bigger than 1, so that means that this series does what? Converge. So I've got the series I don't know about between 0 and a series that converges. So that means that the series in between must also do what? Converge by the direct comparison test. So by the DCT, since the series that it's bounded by converges, so does the series k goes from 1 to infinity of the absolute value and by absolute convergence my original series converges. See how the logic fits? Now there's some other interesting properties of absolutely convergent and conditionally convergent series. Conditionally convergent series have a pretty remarkable property. It's Riemann's rearrangement theorem. That's the same Riemann from Riemann sums. If you have a conditionally convergent series, you can pick any real number you want, and then you can rearrange the series to add up to that number. So here's the alternating harmonic series. We've shown that this series is conditionally convergent. On its own, it converges. It's an alternating series. Alternating series test works. When you take the absolute values, you get the harmonic series, which blows up. All right, so Max, what's your favorite number? 7. Riemann's theorem says you can rearrange the terms in that series so it adds up exactly to 7. Adam, what's your favorite number? 9. You can rearrange those. So it's basically you've got a box in the corner with those terms. 1 minus a half, 1/3 minus a fourth, whatever. You got a box in the corner. You can just pick them out and you can rearrange them to go to anywhere you want in the real number line. You can even rearrange them so they go up to infinity or minus infinity. You go anywhere you want. So when you see the word conditionally convergent, the series converges but the absolute values don't. The reason it's called conditionally convergent is because where it converges to can depend on what arrangement you have of it. So case in point, we're going to find out next week that with this ordering, the series adds up to the natural log of 2. And you can go through this classic rearrangement to get a series that adds up to literally half of what it was before. All right? That's remarkable. But once again, that's one of those things about infinity. Okay? Because with your experience with addition, should it matter the order in which you add things up? No. That's the commutative property, right? A plus B equals B plus A. Not so when you talk about infinite series. That being said, if you have an absolutely convergent series, things are nice. Okay? They're boring, but they're nice. Because every rearrangement of an absolutely convergent series will go to the same place. And this is a property we're going to be using next week quite a bit at the end of next week. We're going to have absolute convergence. That's going to let us do arithmetic the way we like to do arithmetic. All right. Conditionally convergent series, you rearrange the terms, who knows where you'll go. You can go anywhere, right? That's why it's kind of like at Lakeland. If you start here, you can go anywhere. With the alternating harmonic series, you can go anywhere. If I'd have one series at home, it would be the alternating harmonic series.